Hey guys, it's Vince here. Today I'm going to talk to you about Ramsey's theorem. So, Ramsey's theorem is a fundamental theorem in combinatorics which ultimately gave rise to its own field of study, Ramsey theory, which is concerned about um, sort of unavoidable patterns in structures like graphs. So, the classic Ramsey theory question, which I'm sure you've all heard, is if I have a party, how many people do I have to invite so that either three people all know each other or three people all don't know each other? Feel free to pause the video and have a think. All right, so we're going to solve this problem with a graph. We're going to let the vertices of the graph represent people, and we're going to draw a blue line between them if they know each other, and a red line between them if they don't know each other. And it's pretty easy to see that in order to have three people that all know each other, we need to have a blue triangle. And in order to have three people that all don't know each other, we need to have a red triangle. All right, so obviously if I invite three people to my party, I might have a triangle like this. Therefore, three people don't necessarily all know each other or not know each other. All right, what about four? So if I invite four people, the question becomes, is it possible to color all the edges of this graph in so that I don't have a blue or red triangle? Well, let's see. If I color all the outside edges blue and the diagonals red, then yeah, easy. I've got no blue and no red triangle. Okay, what about five? So if I invite five people, then let's try following the same technique. Let's color the outside edges blue and the diagonals red. So, yeah, perfect. We actually don't end up with a blue or red triangle. You can take a second to look at it, verify it yourself, but it's got to be bigger than five. Okay, so we need to be inviting at least five people to our party in order to have three people all knowing or three people all not knowing each other. So I claim the answer is actually six. And I'm going to show you why. So if I've got six people at my party, I'm going to let these vertices represent the people. Then all we have to do is just look at this one person over here. Okay, so there's not that many scenarios which could actually happen. And what you notice is you're always going to have at least three lines of one color coming off this person. So this person is always going to know at least three people, or if they don't know at least three people, then they're going to not know at least three people. So without loss of generality, let's just assume that they don't know three people. Okay, the same argument could be made if it's three people they do know or more. So if they don't know three people, then in order to avoid having these red triangles here, these people have to know each other and these people have to know each other. And actually, these people have to know each other. But if I draw a blue line in there, then I'm going to have a blue triangle. So what we find is that no matter how you try and color in this graph, have a go at it. No matter how you try and color it in, you will always have either a blue triangle or a red triangle. So that means that I have to invite 6 people to my party in order to guarantee that 3 people all know each other or 3 people all don't know each other. So what does Ramsey's theorem actually say? Well, Ramsey's theorem says if you're given any 2 positive integers, x and y, then there exists a positive integer, we're going to call it r of xy, which is the smallest integer such that if you color the edges on the complete graph with r of xy vertices using 2 colors, then you're guaranteed to have a subgraph kx or ky that is 1 color, either red or blue. So in our example above, we solved r of 3 equals 6. This means that if you're coloring your complete graph using 2 colors, the smallest one that you need to have so that you always have either a red or blue triangle is 6, the complete graph on 6 vertices. Now, this theorem actually generalizes in a really nice way. So here we were doing it for 2 colors. You can actually do it for 3 colors. So r of 3 equals 17. So what this means is that if you instead now you're coloring your complete graph with 3 colors and you're still trying to avoid triangles, you're guaranteed to have a triangle of one of the colors if you've got 17 vertices. Now, not only can you generalize by adding more colors, but instead of having these numbers in here, so here in these examples, the 3, that actually represents K3, the complete graph on 3 vertices, which is just the 3 cycle. Instead of this, you can actually ask the question, what is R of GH, where G and H are any simple connected graph that's connected up however you want. Okay, these can be any simple connected graphs. And what R of GH answers is, again, it's what is the smallest integer, just like we were talking about above. It's what's the smallest integer such that if you color the edges on K, this time it'll be R of GH vertices, then you're guaranteed to have either G or H as a subgraph that is colored in exactly 1 color. Pretty cool, right? So all in all, Ramsey's theorem is a very general, very powerful theorem that is deeply founded in combinatorics and has really opened up its whole own branch of mathematics to answer any kinds of questions about how big your universe has to be to have some sort of order. In this case, we're talking about how big your complete graph has to be in order to have certain subgraphs inside it if you try and color it using different colors. If you have any questions, let me know. Thanks for watching.